Looking at a fusion reactor sputtering out and failing to ignite, you're probably reminded of the headlines we've seen for a decade. 5-minute EV charging, permanent cures for genetic blindness, infinite clean energy. We are told these breakthroughs are always just around the corner. But for most people, the daily reality is different. Phone batteries still degrade, the power grid remains fragile, and chronic diseases are still managed rather than cured. It feels like the promised future is on perpetual backorder. This delay didn't happen because we ran out of ideas or funding. We stalled because our best theoretical science collided with the stubborn, literal limits of physics and biology. We can write algorithms and sketch blueprints all day, but imagination does not dictate the pace of human progress. Hard physical constraints do. Take gene editing. For years, powerful tools like CRISPR were physically too large to fit inside the tiny, hollow viral vectors needed to carry them deep into the human body. In computing, AI models required constant human supervision to correct hallucinations, while quantum computers struggled to scale because their data gates were simply too error-prone to function. In energy, solid-state batteries worked in the lab but couldn't survive mass production, and experimental fusion reactors kept inexplicably melting their own exhaust systems. In early 2026, across fields that rarely overlap, researchers began reporting a series of nearly simultaneous breakthroughs that directly addressed these historic bottlenecks. 2026 marks the threshold where the scientific community reached the engineering limits of these fields, moving these technologies out of the laboratory and into industrial production. The first shift was a matter of scale. An NIH-funded team discovered and engineered a naturally occurring enzyme called Al3-Cas12F. It is compact and essentially comes pre-assembled. Because this microenzyme fits perfectly inside viral vectors, we can send CRISPR directly into the body. It achieved 90% editing efficiency on previously unreachable targets. This microscopic mastery extends to hardware. Applied Materials has entered the angstrom era, building 2-nanometer chips with atomic-level precision. Mastering engineering at this scale allows us to treat human biology and computer hardware with the exact same manufactured precision. While manufacturing mastered size, software mastered autonomy. The enterprise world is currently transitioning from basic chatbots to agentic AI. Google's Aletheia system demonstrated this by solving 6 out of 10 novel, unpublished mathematical proofs. It did this completely autonomously without a single human hint. This loop is how the human bottleneck was removed. One AI node generates a solution, a second verifies it for flaws, and a third revises the work. It checks its own logic and fixes its own mistakes. This is already operational. Mizuho Financial Group launched an agent factory that successfully reduced the time it takes to deploy banking AI from 2 weeks down to just days. AI functions as a self-correcting, autonomous workforce capable of scaling its own output and operations independently. With intelligence scaling digitally, we finally address the chaotic physical forces that have kept advanced energy stuck in the research phase. Greater Bay Technology has moved solid-state batteries into mass production. These cells charge to 80% in 7.5 minutes and operate without the liquid electrolytes that historically limited their scale. In macroenergy, physicists at Princeton solved the mystery of why superheated plasma was destroying the exhaust systems in experimental fusion reactors. By factoring in plasma rotation alongside sideways drift, researchers can now match simulations to reality. We can finally build magnetic fields that ensure the plasma misses the exhaust walls entirely. In quantum computing, ParityQC doubled the capacity of current systems. They successfully ran a 52-qubit system on IBM hardware by bypassing the error-prone gates that previously caused computations to fail. Solving these chaotic physical forces, from rotating plasma to unstable qubits, provides the foundational reliability required for the next generation of energy and computing. Over the next decade, these specialized victories will change the baseline of daily life. Diseases like ALS, blindness, and dementia will move from lifelong management to one-time genetic and neural treatments. In infrastructure, solid-state EVs with 1,000-kilometer ranges will arrive in standard garages, effectively ending range anxiety. The immediate impact of 2026 is the removal of constraints we once viewed as permanent, from daily inconveniences to previously fatal medical diagnoses. But the true projection for the next 20 years involves these disparate technologies feeding into one another. Autonomous AI agents will soon utilize exponentially scaled quantum computers to run their own advanced research and development pipelines. Those autonomous pipelines will then use new plasma rotation models to deploy optimized commercial fusion grids. Humanity spent the last century theorizing the future, and the last decade hitting physical limits. Because the physical bottlenecks are now being addressed, the next 20 years will be defined solely by how fast we decide to scale.